Good morning to one and all. This is Dr. Vijay Kumar, working as an assistant professor in the Department of Mechanical Engineering from St. Peter's Engineering College, Hyderabad. Today I am going to discuss about the combined velocity triangles for the steam turbines, how to construct the combined velocity triangle. Actually, velocity triangles already we studied in the fluid mechanics and hydraulic machines. So topics are in the impact of jets and pumps and turbines. Just here we are combining the inlet and outlet velocities. So how we have to construct a combined velocity triangles, we'll see in the today's class. So before then what is the function of the steam turbine? So steam turbine is the one of the major component in the steam power plant. Here the function of the steam turbine is whatever the heat energy developed in the boiler is converted into mechanical energy. So further, with the help of the generator, the mechanical energy, generator is attached to the turbine. With the help of generator, a mechanical energy further converted into electrical energy. So a steam turbine is a prime mover in which the energy available in the steam is directly utilized to rotate the turbine rotor. So here the high pressure, high temperature steam from the boiler is expanded in a fixed nozzle where the enthalpy drop is converted into kinetic energy, and this kinetic energy of jet impinges on the blades mounted on the rotor, and change in the direction of jet give rise to change in the momentum to provide torque on the rotor. So let us see the torque on the rotor. For example, it's a vane or it's a blade. This is the jet direction. The jet direction is the absolute velocity at inlet, and here the jet direction, jet flows tangentially to the curved vane. Why? Because the tangential flow is due to avoid the frictional losses. So V1 is the absolute velocity at jet inlet, and VW is the tangential component of V1 or wheel velocity at inlet. Now for absolute velocity, we have one horizontal component and one vertical component. Horizontal component is the wheel velocity and vertical component is the flow velocity. And so, for example, it is a moving blade. We have to consider the blade velocity. So, if it is a tangential force, is the mass into acceleration, where here the acceleration is the change in the wheel velocity at inlet and outlet. And next, torque. So, for calculating the torque on rotor, we are considering the tangential force into radius of rotor. And now work done on the rotor is equal to torque into angular velocity. For calculating work done on the rotor, for calculating the work done on the rotor, torque into angular velocity, that is omega. So for calculating the work done on the rotor, so m into r into omega into VW1 minus VW2 into, that's it. So, but omega into r is the linear velocity of blade. So that is equal to u. So finally work done formula m into Vw1 minus Vw2 into u. So if a fluid enters a passage at a radius r1 and leaves at radius r2, and u1 and u2 are the rotor velocities at inlet and outlet respectively, then this equation can be modified as m into Vw1 u1 minus Vw2 u2. So it's a inlet velocity of will into blade velocity, inlet blade velocity, initial blade velocity minus will velocity at outlet into final blade velocity. It's moving distance. This equation is also known as Euler's equation. For construction of combined velocity triangle, first of all, draw a horizontal line. Draw a horizontal line and cut off AB equal to blade velocity. So first of all we have to draw a horizontal line and cut off AB equal to velocity of blade to some suitable scale. Now at B, draw a line BC at an angle alpha with AB. So here angle is the alpha, and now cut off BC is equal to V1, so that is velocity of steam jet at the inlet of the blade to the scale. Join AC which represent relative velocity at inlet. Now at A, draw a line AD at an angle phi with AB. Now at so with high angle, draw a line A at an angle pi with AB. Now extend the AB line. Extend the AB line, draw a perpendicular line from C. Now it is the CE represents the flow velocity. Actually now the inlet velocity triangle will be completed. Then we have to draw the inclined line with AB with a phi angle, draw an inclined line. Now with A as a center and radius equal to AC, draw an arc in meeting the line AD. So now it is D. So means here AC is equal to AD or VR1 is equal to VR2. Why? Because here we are not considering the frictional losses. Here we are neglecting the friction due to neglecting the frictional losses in the nozzle. Here there is no change in the relative velocity at inlet and outlet. So here relative velocity at inlet is equal to relative velocity at outlet. So this is the VR2. Here AC equals to AD. Now join BD and extend the AB line and draw the perpendicular line from the D. Now it is F. So triangle AFD is the outlet velocity triangle. So the arrow is same. So V2, VF2. Now combined velocity triangle is completed for the impulse turbine for considering the frictionless. If we are considering the friction, the construction position of the combined velocity triangle same for the construction position of the inlet velocity triangle is same for both the frictionless and friction. So for example, now I have completed the inlet velocity triangle. So first, what's the procedure? First we have to draw the horizontal line that is equal to blade velocity and draw the inclined line with angle alpha with AB, and line BC is equal to inlet jet velocity, and extend the AB line up to E and draw a vertical line from C. So that is the flow velocity, and EB is the wind velocity at inlet. This is the construction procedure of the inlet velocity triangle. While we are considering the frictional losses, here due to friction, we have due to enthalpy drop, due to friction, the steam flows through the wall of the nozzle. Due to friction, there is a loss in the velocity. So it may be 10% or 20%. It depends upon the nozzle shape and the condition of the steam. So for example, so C dash. C dash. So while comparing the friction and frictionless, so first figure shows the frictionless. Here we are not considering the friction. In an impulse turbine, the relative velocity at the outlet is same as relative velocity at inlet. But in practice, there will be a frictional resistance to the flow of steam jet over the blades. As a result, there is a loss of relative velocity. Considering friction, VR2 is equal to K VR1. So where K is the frictional or velocity coefficient. If there is 15% loss in relative velocity, then the value of K is 0.85. Actually, K varies from 0.75 to 0.85. In this figure, C dash distance is the loss of velocity due to frictional. So here AC dash is equal to AD. Now A as a center, C from AC radius, draw arc. Now it is D. Here AC radius, we have to draw the arc. But here AC dash, why? Because we are considering the frictional losses. So C dash is the frictional losses. So from AC radius, draw arc, remaining procedure is same. Join DB and draw the perpendicular line and extend the AB line. Now it is F. So there is no change in the any other. So procedure is same for both. Only difference is here we are not considering the frictional losses. Here we are considering the frictional losses. So now this is the theta blade inlet angle. Now it is the beta jet outlet angle. So here we are to V2, VF2. So construction provision is almost the same for the both in practical, and it is a theoretical. Combined velocity triangle for whenever we are not considering the friction, when we are considering the friction. That is the differences. And next, now, so we have completed the combined velocity triangles for the impulse turbine. Now let us draw the combined velocity triangle for moving blades of the reaction turbine. So first of all, here also we have to draw the horizontal line. So that is equal to AB, that is blade velocity. Now at B, draw a line BC. Draw a line BC at an angle alpha with AB. Similarly at A, draw a line AC. Draw a line AC at angle theta. At an angle theta with EA meeting line meeting the first line at C. Now CA and BC is represent relative velocity at inlet and absolute velocity at inlet, and CE is the flow velocity at inlet. Now inlet velocity triangle is completed. Now at A, draw a line AD at an angle pi. At an angle pi. Here pi is equal to alpha. So here, in case of the reaction turbine, the outlet blade angle is equal to inlet absolute velocity angle. Why? Because in reaction turbine, we have in turbine casing we have attached the fixed blades. So the steam first flows through the fixed blade, then glides over to the rotor. So here the exit of the fixed blade angle is the inlet of the moving blade angle. So draw the AD line with an angle pi which is equal to the alpha. The remaining join BD, and here theta is equal to beta. So VR2, V2, VF2. Now VW1, VW2. So here pi equals to alpha, theta equals to beta. Then it is now EB is the Will velocity at inlet and BF is the Will velocity at outlet, and C is the velocity of flow at inlet. VF2 is D. DF is the flow velocity at outlet. Now it is beta, alpha, pi, theta. So theta and pi are the inlet blade angle and outlet blade angle. Here fixed blade angle means guide vanes. These are the fixed, actually in case of the Parsons reaction turbine, the fixed blades are attached to the casing, already we discussed. So, well, a careful study of the combined velocity diagram of Parsons reaction turbine will reveal that it is symmetrical about the central line. Therefore, VF1 is equal to VF2. So means here flow velocity due to symmetrical about the central line, VF1 is equal to VF2 and V1 is equal to VR2. Here inlet velocity is equal to VR2. Where in case of the impulse turbine, VR relative velocity at inlet equals to relative velocity at outlet when we are considering the frictionless. But in case of the Parsons reaction turbine, here absolute velocity at inlet is equal to relative velocity at outlet. Why? Because here pi equals to alpha. And similarly, VR1 is equal to V2. So here relative velocity at inlet is equal to absolute velocity at outlet, because here theta equals to beta, and here EA distance is equal to BF. EA distance is equal to BF due to symmetrical about the center line. These are the construction of the combined velocity triangles for impulse turbine and reaction turbine. So next class we'll solve the example problems in the steam turbines with the help of the combined velocity triangles. So how much power will be generated the impulse turbine, or in case of the reaction turbine with the help of the combined velocity triangle we can calculate it. Thank you, Ananda.